Okay, so I hope my screen is also visible. So let's start our today's class. This is lecture 19 on computer networks, and in this lecture, we are going to resume our previous lecture only. And in the previous lecture, we were discussing TCP. Okay, and I have told you that it is connection-oriented protocols. See this. Okay, and there are three phases. That is connection establishment, then data transfer, and then connection termination. We have studied all these three phases in the previous lecture itself. With proper examples we have done this. Okay, and in the header itself, see this, in the header, till what point we have covered, let me show you. So header length reserved, so urgent flag we have to do today. So ACK flag, fin flag, ACK flag, SYN flag we have completed. So now three flags are left: push flag, RST flag, and URG flag. So I will complete these three flags. Okay, and then slowly we will dig deep into the topics. Okay, yeah, so let's start our today's class. So first of all, we are going to study about push flag, PSH. PSH is push flag. Push flag. Okay, so what is push flag? See, generally TCP will wait for one MSS. Okay, see, application layer is sending data byte by byte to the TCP. Okay, and now this TCP, it will generally wait for one MSS. One MSS is maximum segment size, which we have studied in the previous lecture itself. So TCP will wait for one MSS, and then it will make segment. That means this is the data from application layer. Okay, and then it will attach the header transport and make a segment. Okay, and then this segment will be given to IP. It will make that datagram and so on. It will travel through the internet. So generally TCP will wait for one MSS. Now question arises, why it wait for one MSS data? That means if application is sending only one byte by byte it is sending now. So why it is not making segment of just one byte? Okay, let me answer that also. Take the snapshot. Okay, so what? Okay, let me check. I think voice is a little bit less. Let me check it. Yeah, so I think it's okay. Yeah, so I was telling you that why it is not making one byte segment. So question is, why not one byte data in the segment? Okay, that is the question. So answer is very simple. So if you want to transfer only one byte data, then header transport will be of 20 byte. Then header network will be of 20 byte. And then forget about data link layer. Data link layer also will add some header and so on. So you are adding 40 byte overhead for one byte data. Okay, and it is not sufficient. 40 byte you are adding, segment will be sent, and then ACK will also come. Now ACK will also have 40 bytes. So 40 plus 40, 80 bytes. So 80 byte overhead for one byte data, it is not good. Okay, if you calculate the efficiency will be useful data is only one byte, and total data is 80 plus 1, 81. So 1 upon 81. So it is very less efficiency. Okay, so efficiency is very less. So generally we are not sending one byte of data in segment. Rather TCP will wait for one MSS data. Okay, and then it will send, it will make a segment and then it will send. It is just like that. This is a truck. TCP is a truck. Okay, so in truck if you send only few grams or few kilograms of some raw material, then it is of no use. Okay, you are simply wasting diesel and you are simply wasting manpower in that. Rather you just completely full the truck and then you send it. That is the basic idea we are using here. So you should send one MSS data. Okay, you should wait for data from application layer. Okay, for one MSS data, and then you should send it. Rather TCP will send only one MSS data. Okay, yeah, this is the basic scenario. Now but in some scenarios, for example, we have some interactive application. Okay, for example, chatting, you are doing chatting with somebody, so you will send hi. Okay, and then he or she will send hi and so on. So you are sending just 2 byte of data. Okay, and now if TCP wait for 1 MSS, okay, and then only it will send the data, then you are not doing chatting, you are sending an email, like you'll send hi, how are you, I want to say this, that, and so on. So you will make one email. Okay, so it will not look like interactive application, you are not doing chatting, you are sending an email, it will just look like an email. Okay, so it entirely depends on need. So sometimes TCP want to send 1 byte or 2 byte data. Okay, it is not like that it will send 1 MSS always. So sometimes there is a need to send only 1 or 2 bytes of data. So in that scenario we will use push flag. Are you getting it? So whenever TCP want to send very small amount of data, then push flag will be set. Is it okay? Take the snapshot, I will jump to the next slide.
The previous slide I was going to say.
Okay, previous, okay, take it.
Yes, sir.
Okay, this also?
Yes, sir.
Okay, so now what we will say, application layer, it will send 1 byte. Actually, see, TCP is just a medium. TCP is a truck which is taking the data. So you are the one who is, or application layer is the one who is, you can say, making the data, or who is actually creating the data. So application layer will send push request. Okay, application layer will send PSH request, push request to TCP. Okay, it has sent just 1 byte. It has sent 1 byte. Application layer is sending 1 byte to TCP. Now TCP generally wait for 1 MSS, but now application layer has sent push request to TCP. So now what TCP will do? It will send only 1 byte of data, and it will make header transport, and it will make a segment. So segment containing only 1 byte. Segment containing only 1 byte. Okay, so it will send it to receiver. So are you getting it? Application layer will send push request. Okay, TCP will make 1 byte segment, segment containing only 1 byte, and it will send. It will set push flag. It will set push flag. Now important point is coming. Try to listen carefully. So application layer has sent push request to TCP. Now TCP will not wait for TCP not wait. TCP not wait for MSS. Okay, it will simply make one segment containing only 1 byte, and it will set push flag. Okay, now TCP will set the push flag. So now at the receiver side, when receiver TCP, okay, this is the sender side, and now at receiver side we have a circular buffer. Now both sender and receiver has circular buffer. Okay, I have told you. So in this buffer, obviously it will be placed at the end. Okay, so it is, let us suppose this 1 byte of data is placed here. Now receiver TCP will see the push flag is set. Push flag is set. So now what it will do? It will push this entire data to application layer on urgent basis. So generally TCP will wait for few data bytes, and then it will push that to application layer. But now as the push flag is set, so receiver TCP will push this. So there is some data. So all this data along with this 1 byte will be pushed to the application layer. So application layer will receive the data in sequence. This is important. Receive data in sequence. So you can imagine it just like an ambulance. Okay, so ambulance has come, there is a red light here. So what we will do, so every car which is ahead of ambulance, they will break the red light and they will go, so that ambulance can go. Okay, so red light is now does not matter, because there is an ambulance here. So same is the scenario here. Push flag is set. Receiver TCP will say, okay, push flag is set, so I have to deliver all the data. I will not wait unnecessarily. I will deliver all the data in sequence to the application layer. So like you can say ambulance cannot fly now. Ambulance cannot fly. Ambulance will be you can say will be behind these 3 cars. Okay, it cannot fly. So that's why it will receive data in sequence. Application layer will receive data in sequence whenever push flag is set. So now you have got the idea why push flag is used. So application layer will send push request at the sender side. Now TCP will because application layer send push request, so now TCP will not wait for one MSS. It will make one segment containing only one byte, and it will set the push flag. Why now you have got it. Why sender has set the push flag, so that receiver TCP get idea. Okay, this is you can say this data should be given on urgent basis to the application layer. So it now receiver TCP will not wait for some other data. It will push the entire data to the application layer. Okay, so so application layer will receive data in sequence. So I hope you have got it now.
Yes, sir.
Okay, so this is push flag. Take the snapshot. I will jump. So basic scenario is receive data in sequence. It is important. Okay, in sequence delivery. In sequence delivery. So I will use this word. They will ask this question: in sequence delivery on urgent basis. In sequence delivery on urgent basis. This is done by push flag. Okay. Take the snapshot. I will jump to the next slide.
Done, sir.
Okay. So next is urgent flag. Push flag is over. Now we are going to study urgent flag. Urgent flag is also same. So what it will say, application layer is sending data byte by byte. So now application layer will send urgent request, URG request to the TCP. So now TCP will take only one byte. Okay, let me clear this. So TCP, so application layer send just one byte. Okay, application is sending byte by byte. It has sent just one byte, and it has sent urgent request. So what TCP will do? TCP will send this one byte of data, and then it will attach header transport, and it will make the segment. Okay, and then it will be transferred to the receiver side. Okay, so now same just like push request, application layer will now send urgent request. So now TCP will make one segment. Okay, and in this it will send set urgent flag, set URG flag. Okay, now at receiver side there is a circular buffer. So in the circular buffer, this data will be placed at the end. For example, here 1 byte data, and there are some other bytes also. So now what it will do, urgent flag, as the name suggests, it is very urgent data. So what TCP will do, receiver TCP, this is the application layer. So it will send this only 1 byte to the application layer. That means out of sequence delivery. So for in sequence delivery, push flag. For out of sequence delivery of urgent data, use URG flag. Okay, so out of sequence delivery of urgent data, use URG flag. So you can imagine, it is just like, you can imagine that ambulance can fly now. Ambulance can fly. So in previously I have told you ambulance cannot fly. Ambulance will come just after these 3 cars, but now ambulance will fly away and it will be given to application layer. These 3 cars are at the same place only. Now ambulance has wings, so now ambulance has opened the wings and now it has just fly away from the red light. Okay, so this is the scenario for urgent flag. Yeah, so now so for push flag I have given you the application, that why we need push flag and all, because we want to do chatting with somebody. So we do not want to write, we do not want that it look like an email. Okay, you are doing interactive application, you are sending hi, he is sending hi, then you are sending how are you, he is sending how are you, and so on like that. Okay, but if TCP wait for one MSS, then your entire data will be sent at once, so it will look like an email. I have given you the application. Now what is the application of this urgent flag? Okay, for example, you want to send data for sorting. Okay, so from client is sending data to server to sort some data. or to sort some numbers. Now client come to know, okay, I have given wrong numbers, so I should give correct numbers. So for that it will send urgent flag, and it will say in that please terminate the connection, or it might say like I will send other data and so on. I'm not going into details of all these things, how this will be sent and all. It is not required for gate. I'm just giving you an application. Okay, so application is that on urgent basis now you want to send to application layer na, that data you are processing is wrong, I am sending new data, please try to process that data. Okay, so I hope you have got it.
Yes, sir.
Okay, so this is urgent flag. Okay, so ambulance can fly, you should remember this. And one more point was coming to my mind. And what was that? Urgent pointer field, yes, very important point also here. So if you try to look at say this TCP header, where was that? Yeah, here is the TCP header. So see this source port number, destination port number, sequence number, acknowledgement number, header length, reserved is for future use. So you have studied now urgent, acknowledgement, push, RST I will tell you, syn fin, window size I will tell you, checksum I will tell you, urgent pointer field. See this. So what is this field? Now I am going to tell you that. Okay, so it is related to urgent flag only, that's why I'm telling you here itself. So next is urgent pointer field in TCP. Urgent pointer field in TCP. So it will tell you about till what point urgent data is there. Okay, so segment it is not like that segment will contain only urgent data. Segment might contain urgent data as well as your new data also. For example, you are send some numbers and you are saying that these numbers are wrong, I want to send new data. Okay, so till what I am assuming that till this point urgent data is there, and then this is URG urgent data in the segment, and then you are having some normal data. Okay, so this is normal data, that means for which you want in sequence delivery, but this is out of sequence delivery. Okay, so this is the header transport. Now question arises, how receiver TCP will come to know till what point this urgent data is there. Are you getting it? So the beauty of urgent data is that TCP allows to say it is not sending only urgent data, it can send normal data and urgent data mix in one segment also. Now in that scenario, how it will come to know that till what point it is urgent data? So for that we have urgent pointer field in TCP. Okay, so urgent pointer will tell that till what point it is urgent. Okay, so for let me tell you that, for example, and obviously urgent pointer field is valid. It is valid only when urgent flag is set. It is valid only when URG flag is set. Okay, if that flag is not set, then obviously this field is not valid, or you receiver TCP will simply ignore the value of this. Okay, so it is valid only when urgent flag is set. Okay, now I'm assuming some urgent data is there, some normal data is there. So for example, I will simply solve a small numerical. Sequence number is say 1000. URG pointer is say 100. So I will say till 1100 byte. Till 1100 byte we have urgent data. Okay, so 1000 plus 100, that is 1100. So till 1100 byte we have urgent data. So how many bytes? You might get confused. Total 101 bytes are there. It is not 101. Why? Because sequence number 1000 means first byte number is 1000, then 1001, 1002 till 1100. So 1000 to 1100, total 101 bytes are there. Any doubt here?
So urgent pointer, I didn't understand. Sequence number, if it is 1000, and urgent pointer, if it is 100, 100 onwards, that is 101 onwards, the rest of all the things will be?
No. Sequence number is 100 and urgent pointer is sorry. Sequence number is 1000. Urgent pointer is 100. So sequence number plus urgent pointer, you add these two. So I will say till 1100 byte we have urgent data.
All right, sir.
Okay. And sequence number started from 1000. So I will say 1000 byte number 1000, then 1001, 1002 till 1100 we have urgent data. So how many bytes are there? Please come again.
As you wrote 101 here, sir, that confused me actually.
So now you have got it now. How 101 is coming?
No, sir.
Okay, so I am just telling you from 1000 till 1100. These are urgent data. So this is first byte, this is second byte, this is third byte. So till 1100, how many bytes are there?
Yes, sir. Yes, sir.
101 bytes. If you have any confusion, you start with 100. Say 100, then 101, 102. How many bytes are there? 3 bytes. How you have got 3 bytes? 102 minus 100 plus 1. Okay, so 1100 minus 1000 plus 1, that is 101 bytes. So 101 bytes are urgent data bytes.
Yes, sir.
Okay, yeah, so this is all about urgent pointer field. Take the snapshot. I will jump to the next slide.
Done, sir.
Okay, yeah, so the last flag is remaining is RST flag, reset flag. Okay, so let me tell you that also. RST flag is used to RST means reset. Okay, so it is used to terminate the connection. You should know this fact. Terminate the connection. So there is already a connection between sender and receiver, or client and server. There is a connection and we want to terminate that connection. For that we will use RST flag. Okay, so why we need to terminate? For example, say this is a client, okay, and this is server. Okay, now client has request for say very large amount of data, say 4 GB file. There is a 4 GB file which client want to download from server. Now I am assuming that there is a connection between client and server. Only then it has requested a file, and now server will keep on sending file to the client. Okay, now assume that client goes down. Now server is sending segments. It will keep on sending segments to the client. Client is down, and when client is up, that means say shut down. Client has shut down, or some power failure, and something might has happened with the client. And now when again client will come into the picture, what it will see? It will see that many lots and lots of segments are coming from server. Okay, and now client is not able to recall what was there. Why? Because everything is done from RAM, random access memory. Okay, and when power goes, then obviously everything has been gone. So client is not able to remember what was the connection, what was the sequence number, and so on. It is not able to remember. So client will say, hold on, what you are doing? So it will send RST flag. Okay. So it will send RST segment containing RST flag set. Okay, so it will send a segment with RST flag set. Okay, and obviously this it will not carry any data, no data in the segment. Okay, but what should be the data? By the way, it just want to reset, terminate the connection. So this segment will contain no data and RST flag will be set. Now in the previous lecture, if you try to remember, I have told you that there is a SYN flag and ACK flag. Okay, so both are 0. So when say this is 1 and this is 0, it is the first packet, it is the first segment. When SYN flag is say 0, ACK flag is 1, it is third, fourth, or fifth, and so on. If both are 1, then it is second, and if both 0, then I have told you normal operation it is not possible. But SYN and ACK flag both 0, now it is possible. See this, I have told you in RST. I have told you na that there are some special scenarios where SYN and ACK both are 0. Okay, so SYN and ACK both will be 0 when RST flag is set. Why ACK is 0? Because if ACK flag is set, that means what you are acknowledging. So server has sent some data and you are acknowledging that. That means what you have received it. If you have received something, then only you will send acknowledgement. Now that is very common sense. I am telling you something, you are acknowledging, that means you have understood that. That's why you are acknowledging. Otherwise you will stay mum, you will not say anything to me. Okay, so then I will come to know, okay, you are not understanding. So same is the scenario here. If client send ACK means what? Server has sent some data and client has sent ACK. That means server will come to know, okay, it has received it. Okay, so that's why I'm saying that ACK flag will be 0, and obviously SYN flag is also 0 because now you are terminating the connection. Okay, so both zeros is possible when RST flag is set. Yes, so this is one of the scenario in which RST flag is given. Any doubt here?
No, sir, understood.
Okay, take the snapshot. I will jump to the next slide.
Done, sir.
Okay. Another scenario can be, for example, say this is client and this is server. Okay, and server has sent ACK 500. So from client, sequence number should be 500 now, because whatever ACK has been given by server, that means expectation of server is 500. So client will send sequence number 500. Now by chance, because of noise or something, it becomes say 50,000. Okay, now server will come to know, hey, what you are doing? I am saying 500, but you are saying 50,000. What is this? So server will send RST, okay, to terminate the connection. Okay, so this is the second scenario where RST flag is needed. Okay, so take the snapshot. I will jump to the next slide.
Yes, sir.
Done.
Yes, sir.
Okay, so now you can see what we are left with. Let me show you the header. So now window size field. Okay, so now we are going to study this window size field. So everything is now covered up. You can check urgent flag, acknowledgement flag, push flag, RST, fin, everything is over. Now we are left with window size. So let me tell you that also. Window size field. Okay, what is this window size? Window size is when connection was established, at that point of time, see this, I have told you in the previous lecture that when connection was established, at that time, see this, it has sent window to be 14600 byte. That means a client is having buffer of 14600 byte reserved at the client. Okay, client has reserved 14600 byte buffer, so server can send 14600 byte. Similarly, server also has sent window to be 10,000. That means server has reserved 10,000 byte buffer, circular buffer of 10,000 byte. Okay, so this was the window size. So window size at connection establishment, it will tell about the amount of window or amount of buffer which has been allocated at client and server side. That is the window. Okay, so now from time to time it will keep on increasing or decreasing, okay, depending upon how much data it has sent and so on. Okay, yeah. So and one more thing, and this TCP always work in full duplex mode. Full duplex. Why full duplex? Because client and server can send data simultaneously to each other. Okay, it is not like that client will only send data, server will respond, or server will only send data, client will respond. It is not like that. Both can send data at the same time. So that's why TCP is working in full duplex mode. So client will have both sender window as well as receiver window. Are you getting it? So let me call these systems as A and B, just for you can say simplicity. Otherwise, these abbreviations I will use some other way, and you will get confused there. So I am taking A and B. Okay. So there are two systems A and B which want to communicate with each other using TCP. So WA, it is having both sender window as well as receiver window, and B is also having both sender window as well as receiver window. Window means buffer only. So now A has reserved some bytes, so like 1400 14600 I have told you. So this is the receiver window. So WRA, that means window receiving of A. So now according to window receiver of A, B will make it sender window. So sender window of B. So obviously WRA size should be greater than or equal to WSB. Please let me know if you have any doubt.
Yes, sir.
So obviously if B sender window is more, then it can send more data, so obviously A will be overwhelmed na. So it's better that window receiver A should be greater than or equal to window sender B. Okay, similarly window sender A, so window receiver B. So window receiver B, it is like 10,000 byte B has allocated. Okay, so now according to window receiver B, A will make window sender A. Okay, and obviously window sender A should be less than or equal to window receiver B.
Yes, sir.
Okay, so this is very simple scenario. So this we are going to use. Now for simplicity, otherwise it will become very difficult for me to explain all the things. For simplicity, I will assume that only A is sending data to B is only sending acknowledgements. Take the snapshot. In the next slide I will tell you this.
Done, sir.
Okay, so for simplicity, okay, we assume A to B data only. Okay, A is sending data to B is only sending ACK, B is only sending ACK. Okay, so now what, say for example A and B. Now I will make timeline diagram. Okay, yeah, so assume that this B has at B 1000 byte buffer is available, so it will send window size to be 1000. Now this window size is the field in the TCP which I have told you. Okay, so window size now it will set to be 1000 because at B 1000 byte buffer is there. Okay, 1000 byte buffer is empty, so B will send window size to be 1000. Any doubt here?
No, sir.
Okay, so window size field will contain 1000. Now assume A is having only say 500 byte data, so A will send assume 500 byte data. Okay, so now what will be scenario at B? So 500 byte will be full and
Yes, sir.
500 byte will be empty. So now what we will send? We will send in acknowledgement, it will send window size to be 500 because now only 500 byte data is available.
Yes, sir.
Okay, so now what A will send? Now A will send, let us assume it send only 200 byte data. So what will be the scenario at B? 500 was already full.
700.
500 byte was already full. Now 200 or more come, so only 300 byte is available. So now what B will send? B will send window size to be 300. Okay, so now this is very important. So in TCP header, many students get confused here. In TCP header we have window size field. Window size field is not telling about size of the segment. Size of the segment, there is nothing called total length or something in segment. Okay, rather from network layer we will calculate the total length. I have told you in the previous lecture only. Okay, so window size means window size is not related to total length. Window size means at receiver side how many bytes buffer is available. Now it might be the case that segment size is say 1000 bytes, but window size is say 50 only. Why window size 50 means? Window size 50 means only 50 bytes of buffer is available. See this now. Window size was 1000, so it has sent only 500 byte data. So now B has sent only window size to be 500 and it is not sending any data. So it is just sending acknowledgement. So segment size is very small, but still window size is 500. So the total length, window size is not related to length of segment. You should know this fact. Okay, many students get confused here. Okay, so window size 500 means at B 500 byte you can say buffer is available. Okay, now 200, now it has sent window size to be 300. Okay, now assume that it has yes, 300 was available, but let us suppose it has sent only 100 byte data. So now what will be the scenario? 500, 200, 100, and now only 200 byte is available. Okay, but now assume that 500 and 200 byte is given to application layer. Okay, so total how much? Only 100 byte is you can say used. 900 byte is available. Are you getting it?
Nice, sir.
Okay, so what I am saying is 100 byte it has sent, So total 200 byte was available,
Yes.
but before sending this acknowledgement containing 200 byte, at the receiver side, this 500 and 200, these are given to application layer, because ultimately TCP will give data to the application layer. So 500 and 200 byte is given to application layer. So now only 100 byte is now used, 900 bytes are empty. Okay, so what receiver will send? Now it will send a window size to be 900.
900.
Okay, so it will send 900. Now assume sender send entire 900 byte data. 900 byte. So now 100 was already used, and 900 is also used now. So how many bytes are available? Only 0. So what receiver will advertise? It will send window size to be 0. Okay. So now this window size to be 0. What does this mean? Indirectly, it is giving warning to A, please do not send data. Okay. It means indirect warning to A to stop sending data. Okay. Yeah. Now question arises. Now very interesting question will come into the picture, that till what point it will not send data. Okay, that is the interesting question. Till what point it will not send data? Because A want to send data. A is having very large amount of data and it want to send to B. Now, but B has sent, please stop. I will not able to accept the data. Till what point A will not send data? Let me answer that. Now question is, till what time A will not send data? Okay. So answer is very simple. Till see this, if B has processed some data, then obviously it will send window size to be non-zero. Like window, say if it has like 500 byte data it has consumed, or it has sent 500 byte data to application layer, then after some time it will send window size to be 500. Okay, so obviously the communication will again start. Are you getting it? So assume. Okay, so I will say one possibility is till receiver send ACK in which window size is some positive number. Till receiver send ACK in which window size is some positive number. Okay, it is some positive number. That is when receiver side till receiver send ACK in which window size is some positive number. So here receiver is B na. I will write in bracket B. Receiver B send ACK in which window size is some positive number. So that is after B send some data to application layer, after B TCP. After B's TCP send data to application layer, then buffer is you can say then small amount of and then buffer is having some free space. Buffer is having some free space, so it will so B will make ACK and send it to A. Okay. So B will send ACK containing that amount of free space. I think you have got it now. So till what point A will not send data? Till receiver, that is B send ACK in which window size is some positive number. That is after B. So what do you mean by some positive number? So I'm telling you that if it has sent some data to application layer like 500 byte. So that is after BTCP send data to application layer, then buffer is having some free space. So B will send ACK containing that amount of free space. So let us suppose after some time it send a window size to be 500. So now again communication will start. Okay, so there is no confusion. Now problem arises, what if this ACK is lost? Okay, so now question is, What if that ACK is lost? Now there will be a kind of deadlock because B has sent window size to be 500. So now B is expecting that A will send segment of 500. But A is also expect because ACK is lost. So A will keep on waiting because B has just given him warning that do not send more data. So B will keep on waiting for A will keep on waiting for B. So there will be a deadlock. Are you getting it? So
Okay.
what if that ACK is lost? So B will keep on waiting for data. We will keep on waiting for data and A will keep on waiting for ACK. Hence deadlock. So there is a deadlock. So now what is the solution? Let me tell you. Take the snapshot.
Done, sir.
Okay. So now solution. Solution
So
is
what I wanted to ask you in the previous slide. So why is the last window size is turned 500 again, sir?
I am assuming that it has given 500 byte data to application layer.
Done, sir.
So 500 is available. So let me draw that. Okay.
Done, sir.
So assume 500 byte data is there and 500 byte is empty. So that's why it has sent 500.
Yes.
Okay. So now okay. So take the snapshot.
Done, sir.
So now what is the solution? Solution is now very simple. Solution is for solution for what? Deadlock. We are having a deadlock. So what is the solution? Solution is to maintain a persistence timer. Persistent timer. Okay. At sender side. Okay. So what we are saying is, so this is say A and B. So if B has sent window size to be 0. Okay, so now A has to wait now. So as soon as it send window size to be 0, so A will start PT timer, persistence timer. Persistence timer. Okay. So when this persistence timer expire, then forget about acknowledge. See, if acknowledgement has been received, like say B has sent window size to be 500. Now everything will start normal application, normal you can say communication will start. Okay, but what if this has been lost, window size of 500, acknowledgement has been lost. Okay, or B or you might say that B has not sent this acknowledgement. Why? Because buffer is not yet emptied. Okay, there is no free space at B, so why it will send ACK? So now there are two scenarios. Let me clear you that. Okay, so persistence timer will handle both the situations. First situation is B buffer is not yet empty or there is no free space. Okay, so what will happen? Let me tell you that. So A and B. So the moment window size is equal to 0, A receives window size to be 0. So A will start persistence timer, PT timer. Now if in between that PT timer window size some positive number come, then normal communication will start. But if this window size 500 acknowledgement has been lost or there is buffer is not yet empty at B, so what A will do after expire of persistence timer, A will send just 1 byte data. Okay, A will send just 1 byte of data. Okay, so you can imagine that B is sleeping. Now A is trying to wake up B. That's, hey, please wake up. I want to send more data to you. Are you there or not? So it has sent just 1 byte of data. Now I will assume. Now in this scenario, scenario one, I'm assuming. Okay, I'm assuming that WS is equal to 500 lost. Okay, ACK having WS is equal to 500 lost in the medium. So so here buffer of 500 was full and 500 was empty. Now it has sent 1 byte of data, so obviously it will receive that 1 byte of data. So 499 byte is remaining, so it will send ACK of 499. Okay, and then obviously A will receive, and then normal communication will start. Any doubt here?
No, sir.
Okay, now another scenario. What if here no, you can say buffer is not yet empty. Okay, there is no free space at B, so it has not sent this ACK. Now what will happen? Let me tell you that.
So
So
we
A,
don't call it as again as a Windows space. We call it as an acknowledgement of 499, sir.
yes. So it is ACK packet which will contain Windows size to be 499.
Sir.
Windows size to be 499, and it is an ACK packet. Okay, ACK packet will contain Windows size to be 499. Now assume B has sent Windows size is equal to 0, and immediately persistence timer started. And after persistence timer has expired, it will send 1 byte of data. But buffer is full, 0 byte memory. So obviously what it will say, B will discard it. Obviously when there is no nothing, no space here, so how it will accept it? So it will simply discard 1 byte, discard 1 byte data, and it will again send Windows size to be 0. Okay, so now again persistent timer will start and so on, so everything will be there. So generally A is poking B that please, hey, wake up, I want to send more data, so please send me what is your intention, or how many data is available to you, or how many buffer is available, and so on. So for that it will send 1 byte of data, and obviously when buffer is full, okay, there is no memory here, so it will discard 1 byte of data, and it will send again Windows size to be 0. Now after some time it will again send 1 byte of data, then it will send again Windows has to be 0, and so on. But after few rounds, this thing will go away, and they will start normal operation. Okay, any doubt here? Yes, I hope I am audible now.
Yes, sir.
Okay, so you can take the snapshot of this, then I will jump to the next slide. Done?
Yes, sir.
Okay, next is, so this is all about persistence timer. It is important, Gate has asked this question on persistence timer. So persistence timer is related to when window size is 0. Okay, so to avoid the deadlock situation of which in which B has sent acknowledgement containing some positive number, and it has been lost. Okay, so now B will keep on waiting for data, and A will keep on waiting for acknowledgement. So to avoid this deadlock, what timer is used? Persistence timer is used. This question has been asked in Gate. Okay, so you should know these small things, and I have given you more detailed information about what is persistence timer and all. Okay, so this is all about window size field. So let me give you information. So now window size field is over. Window size field is over. Next field is checksum. Okay, urgent pointer is already completed. Next is only one field is left in TCP header, that is checksum, and then options are left out. So let me clear you about checksum also. Okay, so one by one we are clearing all the fields. So now we are going to start checksum, TCP checksum. TCP checksum. Okay, so uh, for calculating the checksum, TCP, it will take header as well as data. Header and data both. Okay, so it will make checksum for header as well as data both. But in case of IP, checksum was for header only. IP checksum for header only. Okay, but TCP checksum is for header as well as data both, and it is compulsory. It is compulsory. Okay, why I'm telling you this is compulsory? Because in UDP, in the previous lecture itself, I have told you for UDP it was not mandatory, it was optional. Checksum was optional. So that means if you send all ones in checksum field, all ones in checksum, that is, it is not valid. This was for UDP. I have told you in the previous lecture. But in TCP, checksum is compulsory. That's why we are calling it as TCP is reliable protocol. I have told you it is a reliable. But UDP was unreliable. Why unreliable? Because in case of UDP, this checksum was not compulsory. It was an optional field. Okay. So all ones in checksum means it is not valid. Okay, so how checksum is calculated and all, I am not digging deep into it because I have already told you in data link layer that how checksum is calculated. But very interesting point is coming. Try to focus here. I have told you in data link layer itself that checksum is not reliable technique. Checksum is not reliable. Okay, because if one added and one subtracted, so sum will be constant, na? Okay, so for example 1, 2 and 3, so 3 plus 2 5 plus 1 6, so these three numbers are sent, so with these three numbers you will send 6 also, that means the sum. So you are checking the sum, that's why we calling it as checksum. So now assume here it become 2 and here it become 1. Okay, so now numbers have been changed but still sum is constant. So there might be the case one is added, one is subtracted. I have told you in data link there also. Then checksum will not be get affected. Checksum will not be affected and you might not be able to detect that error. Okay, that was a very big problem. So directly and directly I want to concentrate that checksum is not reliable. So but still we are using it in TCP. So to get more reliability we will add pseudo header also. Okay, pseudo header. Now what is this pseudo header and why we are calling pseudo means which does not exist. Okay, pseudo file means file which does not exist. So what is pseudo header? Pseudo header means which does not exist. Does not exist means it will not be transferred. Okay, so at sender side pseudo header, it will contain many fields but it will contain SIP and DIP, source IP address and destination IP address. Okay, and other fields are there but we are not digging deep into it, I'm just telling you. So pseudo header will contain SIP, DIP and some other fields. Okay, and while calculating checksum, TCP will add these also, SIP, DIP and something. Okay, so it is just two-way checking. For example, at it might be the case that at a network layer header get corrupted and as and say DIP get changed, destination IP address get changed, so some other computer has received the packet. Okay, but now it won't be detected now because transport layer will simply receive it. So at transport layer also we will calculate this SIP, we will take this SIP and DIP into consideration and we will calculate the checksum. Now there will be some error because checksum will not be same, so we will discard the packet. Are you getting it? Let me tell you that if you have any doubt, see this. So if A want to send packet to B, but by chance it IP you can say header of IP get corrupted and it is received by C by chance. Okay, yeah, so now C will simply receive the packet and it will transfer the packet to application layer. Okay, at C what we are having, network layer will forward the packet to transport layer. Okay, but how transport layer will come to know that it is not my packet? So at transport layer it will do these things, SIP and DIP. It will again for C, for C it will see na SIP and DIP. SIP will be same, DIP is changed, but for it will take DIP of C and it will again calculate the checksum and there will be some error and it will get caught. Okay, it will be caught by C. Okay, so just for two-way checking we are adding this pseudo header. If you have any doubt I will explain it further, otherwise it is not so important. You just know this fact that while calculating checksum pseudo header is also added. And why we are calling it pseudo? Because it is not transported. It is not transported. Yes, please let me know if you have any doubt. Yes, any doubt here?
No doubt, sir.
Okay, then take the snapshot. I will jump to the next slide. So while calculating checksum, you should know one fact. While calculating checksum, TCP will also add pseudo header. Okay, so obviously it will add header TCP data also, everything will be there for calculating checksum, but it will add another header which is known as pseudo header, and this pseudo header will not be transported from sender to receiver. Okay, and receiver side, this pseudo header will be again developed. How it will be developed? Because SIP, DIP, everything will be there at network layer. Okay, so it will be developed and it will be calculated again. Okay, so it is just for two-way checking. Okay, so pseudo header is for two-way checking. Two-way checking of IP. Okay, IP address is same or not, some other wrong receiver has received or not, for that we are doing. Yeah, take the snapshot. I will jump to the next slide. Done.
Yes, sir.
Okay, so now last is options in TCP header. Options in TCP header. Okay, so for one option I have told you in the previous lecture, that was timestamp. So why timestamp was used? When wraparound time was less than lifetime. Okay, when lifetime of the packet was more and wraparound time was less. So in that case we have used timestamp to extend the sequence number. Okay, to increase the sequence number. Okay, next option is window size extension. Window size extension. I have told you window size field will give information about amount of buffer which is empty or which is free at sender at receiver side. Okay, so this is sender, this is receiver. So receiver will send amount of buffer which is free at receiver side to the sender, so that sender can send that amount of data. Now, but beautiful fact is that window size is of 16-bit field. 16-bit means 2 power 16 minus 1, that is 65535. So approximately it is 64 KB. So more than 64 KB receiver cannot advertise. But what if receiver side buffer is more than 64 KB? So for that we will use window size extension field. Okay, so window size extension is used if large amount of buffer is allocated at receiver side and it want to advertise that buffer. Okay, so I hope you have got it. I am not writing just to save the time. You can take the snapshot. I will jump to the next slide. Done. Okay.
Yes, sir.
Yeah, so next is the third. Third is parameter negotiation. Parameter negotiation. So there are many parameters which are negotiated between sender and receiver, like client and server. So client will put, I think I have told in the previous lecture also, while making connection, client will give its own वो सारी अपनी शर्तें बताएगा. Client will tell कि मेरे को ये सब चाहिए and so on, और server भी अपनी शर्तें बताएगा. तो वो सब शर्तें इसमें आएंगी. Okay, parameter negotiation में. And one of the parameter I have told you was MSS, maximum segment size. Okay. Yes. And the fourth is padding. Padding is zeros. Okay, zeros added to make option multiple of 4 byte. Added to make options multiple of 4 byte. Okay, so padding means zeros added to make options multiple of 4 byte. Because it might be the case that these are not multiple of 4 byte, and then obviously HLEN, I have told you the header length field. Header length field HLEN. Okay, it was 4-bit field. Okay, and it was multiplied by 4. Okay, so header length minimum was this, and then it will be this, and it can go up to 4 ones. So it is 5 multiplied by 4, that is 20. Next 6 multiplied by 4, that is 24. So after 20 we need 24. So what if options are of just 2 bytes? So that is 22. 22 byte header not allowed. So I will add 16 zeros to make 24 byte header. Okay, so padding is used. So zeros added to make options multiple of 4 byte. You can take the snapshot. I will jump to the next slide. Done?
Yes, sir.
Okay. Next is retransmissions in TCP. Retransmission in TCP. So very basic thing is, for example, this is sender, this is receiver. So sender has sent say sequence number 200, segment having sequence number 200, and timer will be started. When timeout occur, it will again send the same segment with sequence number 200. Okay, and then obviously receiver has received it, so it will send, say for example, 100 byte segment was there, so it will send ACK. Okay, and ACK number will be 300. Okay, so say same. So I am just telling you that retransmission in TCP will be done when timeout occurs. Okay, so when timeout occurs, then it will retransmit. That is very obvious. Okay, so why timeout has occurred? Because receiver has might send. There are two cases that receiver has sent ACK, but ACK has been lost in the medium. So timeout will occur and sender will send the segment again. Or receiver has not received the segment because it might lost in the medium. So after timeout it will send again. So anyhow, whatever may be the reason, after timeout sender will send the same segment again. Okay, so after some time, so like timeout can be say 10 millisecond. So after sending segment, sender will wait for 10 millisecond. If acknowledgement come, then it's okay, otherwise it will send the segment again. That means timeout has occurred. Okay, so this is one of the scenario for retransmission. Another scenario is like say A and B. Okay, A has sent say window size to be 500. That means it can receive segment of size 500. Okay, why? Because 500 byte buffer was available. Okay, 500 byte buffer was available at B, so it has advertised window size to be 500. Now assume A to B 100 bytes segments are sending, and let us assume sequence number 100. Okay, and it has been received. So it has received from 100 till 199. Now let me write it here. So it has received 100 to 199. Okay, that means 100 byte segment it has received, and obviously A will send next sequence number to be 200, and let us suppose it is lost in the medium. Are you getting it? See this, window size 500 means A will send now five segments of 100 byte each, because I am assuming 100 byte segment. Okay, before receiving acknowledgement it can send this. Why? Because 100 byte buffer is available, so before receiving acknowledgement it can send five you can say 5 segments. Okay, assume 200 is lost in the medium. Okay, and then sequence number 300. Okay, I think I should use another pen. Sequence number 300, it has been received. Sequence number 400 has been received. Sequence number 500 has been received. Everything has been received except 200. So so till 200 to 299 space is blank, and then from 300 to 399 it has received. 400 to 499 it has received, and 500 to 599 it has received. I think you have got it now. 300 to 399, 400 to 499, 500 to 599 it has received. Now since it has received sequence number 100, so it will send ACK now. Now B will send ACK, but before receiving ACK, A has sent these 5 segments. I am telling you again and again because window size was 500, so it will send 5 segments. And why 5 segments? Because I am assuming that 100 byte segment was there. 100 byte segment was there, so it will send 5 segments before receiving acknowledgement. And since B has received 1 segment, so it will send ACK. Obviously, it has received a segment, so it will send ACK. So ACK has been sent, but this ACK come here. Okay, let us suppose ACK come here, and what will be the ACK number? ACK number will be 200. Why? Because now 100 to 199 it has received. Last byte received is 199. So 199 plus 1, that is 200. So ACK will be 200. Okay, ACK number will be 200. ACK number 200. Now since this has not been received, it has lost in the medium. So obviously for that it will not send ACK. But it has received this 300. So what will be the ACK number according to you? Okay, what should be the ACK number? If you think last byte number is 399, 399 plus 1, that is 400. If you think like that, it will send ACK 400. No. If it will send ACK 400, that means what? It has received till 400. Every byte has been received, but in between we are left with some bytes. So it will send ACK again 200. ACK 200. Why? Because last byte received was 199. 199 plus 1, that is 200. No doubt it has received out of order delivery. Okay, but it will not send the ACK 400. It will send ACK 200 only because last byte was this. Now when this 400 has been received, 400 to 499, it will send ACK. Again it will send ACK 200. Because last byte was this. When 500 has been received, it will again send ACK 200. Okay, and it is very logical also. If it has this, it will send 600, ACK 600. That means what? Till 600 it has received all the bytes. But no, it has not received till 600 all the bytes. In between it is remaining. So it is sending like this. So directly and indirectly I want to say ACK number 200 was the first ACK. Now this ACK 200, it is the first duplicate. This is the second duplicate, and it is the third duplicate. So 3 duplicate ACK. Whenever A receives 3 duplicate ACK, regardless of the timer, it will send segment of sequence number 200 again. Okay, so it is known as faster retransmission. Faster retransmission. Yes, please let me know if you are facing any difficulty. Are you getting it? 3 duplicate ACK. Faster acknowledgement when 3 duplicate ACK. 3 duplicate ACK. Now many students get confused, sir. There are 4 ACKs of 200. Why you are saying 3 duplicate? Array, first one is the actual ACK which will come. Now the second one is the first duplicate. Third one is the second duplicate, and fourth one is the third duplicate. So 3 duplicate ACK come, then immediately, regardless of the timer, A will send a segment of sequence number 200. Okay, so this is known as faster retransmission. And when it is done, this question has been asked in GATE. Please try to remember it. For faster retransmission, TCP uses 3 duplicate ACK mechanism. Okay, now from this style, from window, you have got it. We have in DLL we have studied na go back and selective repeat and so on. So I can you can say give you analogy that TCP is using SR, selective repeat. Why? Out of orders, out of sequence delivery is accepted. SR because out of order delivery accepted. Okay, and it is just like GBN, go back and. Why? Because ACK is cumulative. ACK is cumulative. ACK cumulative means, see this, 599. Okay, then it will send ACK 600. ACK 600 means till 600 it has received all the bytes. Okay, yeah. And now please tell me, since sequence number 200 it has sent, so it will receive from 200 to 299 also. Now what do you think? What will be the ACK? Yes, you have got it right. ACK will be 600. ACK will be 600. Okay, why? Because till 600 it has received everything. Okay, Yes, please let me know if you have any doubt. Any doubt here?
No, sir.
Okay, so that's it. So this is all about faster retransmission, that is through duplicate ACK. Okay, and you should remember that TCP is using mix of both SR and GBN. SR because out of order delivery is accepted, and go back and because ACK is cumulative. Why? See this here also you have seen cumulative ACK. 600 ACK we have directly sent. 600 means till 600 you have received everything. Okay. Yes. So you can take the snapshot. We will jump to the next slide now.
Yes, sir.
Done. Okay. Yes. So next is TCP congestion control. It is very important topic. Many times question have been asked. So try to understand it properly. So first of all, we should know what is congestion. What is congestion? So this is a highway. So we will say there is a congestion on the highway. That means I will assume that highway can manage 500 car or 50,000 cars. 500 is very less. So highway can manage 50,000 car at a time. But now on road there are 1 lakh cars. So obviously what you will say, highway is congested. There is a congestion. So same is the case with the network. So there is a limit on number of packets which network can handle. If packets are more, then obviously network will be congested. Okay. So what is the main root of congestion? I will simply say this is a network. So there are senders which are sending the packet, and there are receivers which are receiving the packets. So sender are the producer and receivers are the consumers. So if producer is producing item at a more faster rate than consumer can consume it, so obviously many packets will piled up in the network, and ultimately there will be a congestion. Okay, so if sender are sending at a very faster rate, but receivers are not able to receive the packet on that rate, so obviously many packets will be in the network itself, and then there will be a congestion. Okay, and main reason of packet lost is congestion only. Main reason of packet lost is congestion. Okay. So you can take the snapshot. I will jump to the next slide. Done.
Yes, sir.
Okay. So let us assume we have a big network in which there are multiple routers and all. Okay, and there is a sender and there is a receiver. Now receiver said that my window size is 1 GB and MSS is 1 MB. This is receiver has advertised this to sender. Now sender will say, okay, I can send 1024 segments of 1 MB each. Why 1024? Because 1 GB space is there. Okay, and MSS is 1 MB. So 1024 segments of 1 MB each. But what if this sender, what if this network is not able to, you can say, hold these packets? Then obviously there will be a congestion. Okay, so what if network can't hold these any packets? So then there will be a congestion. Okay, so now my main focus is that if receiver has sent window size to be 1 GB and MSS is 1 MB, then sender should not send blindly 1024 segments of 1 MB each. Rather, it should consider a network into the picture also. Okay. So so what I want to say is sender must send data. Let me write it here. So sender must send data that is equal to minimum of WC comma WR. Okay, WC is congestion window and WR is the receiver window. So receiver window, it has given 1 GB, but let us suppose congestion window is say 500 MB. So how much data sender must send? It can send only 500 MB data. It should not send 1 GB data. That means we will take minimum of WC comma WR. Okay, and why I'm saying minimum, it might be reverse also. Congestion window is say 1 GB and receiver window is 500. Obviously sender must not send 1 GB data because receiver will be overwhelmed in that case. Okay, so minimum we are taking so that neither network nor receiver get overwhelmed. Are you getting it? Why we are taking it minimum? Because we do not want network or receiver to be overwhelmed. Okay, that's why we are taking them to be minimum. So WC is congestion window. Congestion window means maximum data which can be handled by the network. Okay, network can maximum data can be which can be handled by network. That can be handled by network. Okay, at particular time. At particular instant of time. For example, like this time, I'm saying at say what is the time? Say for example at 10:12. At 10:12 p.m. What is the WC value? WC value means maximum data that can be handled by network at 10:12 p.m. That is WC. Okay, that is congestion window. Okay. So now question arises, how you will find this WC? That is for sure. I want a minimum of these two, WC or WR, minimum value I want to take. But now question arises, how you will get this WC value? That is the biggest problem. So, and obviously we cannot find this WC at any particular instant of time because there are many routers in the network and each and every router has a queue. So I do not know how much queue is full, how much queue is empty at each router and so on. So directly and directly I want to say that network capacity I cannot find. Okay, I cannot find network capacity at any particular instant of time. So now what TCP will use? So for that I am going to tell you the scenario. Take the snapshot. I will jump to the next slide. Done?
Yes, sir.
Okay. So now question is how you will find this WC. First of all, I have told you we cannot find WC. Okay, congestion window I cannot find. That is for sure. So now what is the mechanism used by TCP to avoid the congestion? To avoid congestion, TCP uses AIMD. AIMD is additive increase multiplicative decrease algorithm. It is very important algorithm. AIMD algo. Additive increase multiplicative decrease algorithm. Okay. So to avoid congestion, TCP will use AIMD. So now what is this? I will tell you. For example, this is sender and this is receiver. Now receiver has advertised that my window size or WR is say 8 KB. So now for and how this is during connection establishment. Okay. When connection was made, during connection establishment, R send WR to S. R means receiver. Okay, receiver send WR to sender, for example 8 KB. Okay, and for simplicity we will assume that its size always remain fixed, otherwise calculation will be very difficult. So we will assume that it will remain 8 KB only, it will neither increase nor decrease. Okay, yeah. So and okay, take the snapshot. I will jump to the next slide. Done.
Yes, sir.
Okay, so now we are assuming that window size at receiver, WS, window size at receiver is 8 KB, and let us assume MSS, maximum segment size, is also 1 KB. Okay, so directly indirectly I want to say from that everything should be in MSS. So tip, I want to give you a beautiful tip to solve these questions. Tip is that everything in terms of MSS. Okay, and I'm telling you that also window size is 8 KB, MSS is 1 KB. So what you will say finally, window size will be 8 MSS. I think you have got it now in terms of MSS. So 8 KB divided by 1 KB, you will get 8. 8 is what? MSS. Any doubt here? So window size is 8 MSS, and we will assume WC, that means congestion window, to be 1 MSS initially. Initially congestion window will be 1 MSS. We'll assume it. This algorithm is assuming it. So now what will be the window size at the center side? Window size at the center side will be minimum of WC comma WR. Window receiver, this was 8 MSS. I have just told you window size at which has been given by a receiver was 8 KB or 8 MSS. So now window size or window sender side, WS means window sender. A window sender will be minimum of 1,8. It comes out to be 1. So window at the sender side is 1 MSS. Okay, so directly indirectly it means that sender will send only 1 MSS or 1 segment. Okay, and then it will wait for acknowledgement. Okay, yeah. So take the snapshot. I will jump to the next slide. Done.
Yes, sir.
So actually there are 3 phases in AIMD. The very first phase is slow start phase. You just bear with me for 2-3 minutes, you will get everything crystal clear. Okay, slow start phase. Next is congestion avoidance phase. And the third one is congestion detection phase. Okay, slow start, the name is slow start, but actually it is not slow start. Window increases exponential, so I will say exponential increase. In congestion avoidance, I will say linear increase. And congestion detection, just forget about it. I will tell you about it after few slides. Okay, so there are generally 3 phases in AIMD: slow start, congestion avoidance, then congestion detection. Okay, so how it will be done? Let me tell you that. Take the snapshot. Done.
Yes, sir.
So how it will be done? I have just told you sender window size was minimum of WC comma WR. WR was 8, it was 1. So minimum comes out to be 1. So that is where slow start will start. Slow start phase will start. Okay. So 1, initially it will be 1, then it will become 2. Okay, sender will send 1 MSS, then it will send 2, then it will send 4. That means double. It will keep on doubling itself till what? Till threshold has been reached. So threshold is nothing but WR by 2. So 8 by 2, that is 4. So till 4 we have got doubled. Then this is slow start phase. Then we will have congestion avoidance phase. So in congestion avoidance there will be linear increase, 5, 6, 7 and 8 till 8, because 8 was the maximum receiver window size. After that it will remain 8, 8, 8, 8, 8, 8 only. Dot, 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 dot. Okay. So in graph I will say like this: exponential increase, then linear increase, and then stagnant. Okay, because it has received reached the maximum value, it cannot go beyond 8. Okay, yeah. So I will in timeline diagram I will say this: one segment has been sent and it has been acknowledged. Then two segments will be sent. This arrow means two segments, they will be acknowledged. Then four segments will be sent, they will be acknowledged. Then after 4, 5 acknowledged, 6 acknowledged, 7 acknowledged, 7 acknowledged, then 8 and then acknowledged. After that 8, 8, 8, 8, 8 only. Okay, so now why I have drawn it, because many times question have been asked in GATE regarding RTT. One RTT, one segment sent and acknowledgement came. Second RTT, two sent and two received, two acknowledgements received. Then 3, that means 4, 3, third RTT, 4 segments sent and acknowledged. Then RTT number 4, okay, 1, then 2, then 4, then 5, then 6, and then 7, then 8. So this is your fifth RTT, then sixth RTT, and then seventh RTT. So I will say, after how many RTT? After only 6 RTT, we have reached the maximum window size. Okay, that means 8. After 6, now see this, after 6 you have get 8. This is 7th RTT, no doubt, but you will take after 6 now. After 6 you have got 8. So if you do not want to make this diagram, you can say like this also. What we have done: 1, 2, 4, 5, 6, 7, 8. One RTT, second RTT, third, fourth, fifth, sixth. So I will simply say after 6 RTT, window will reach at maximum value. After 6 RTT, window reach maximum value. Okay, so it's very simple, nothing is there. So you will start with 1, that is for sure. Okay, in GATE exam they might say that start with 2. They will give you some hints, from that you will come to know, okay, that we have to start with 2 also. Don't worry, whatever may be the value, whatever may be the case, 1 or 2. So they will say like slow start phase, start with 2 MSS. Okay, then you cannot fight with GATE exam, they are saying 2 MSS, then okay, you will start with 2, 3, 4, okay, and so on. Like then what I will say, slow start, you will start with 2, then 4. Okay, then because threshold was window receiver was 8 maximum, 8 by 2, that is 4. So 4 we have reached. So then we will start say we will enter the congestion avoidance phase. Then it will be 5, 6, 7 and 8. So after how many RTT? 1, 2, 3, 4, 5. So after 5 RTT we have reached the maximum values. Okay, these are the type of question which have been asked in GATE many times. So they will say slow start phase start with 2 MSS. Don't worry, you will start with 2. They will say slow start phase start with 1 MSS. Don't worry, you will start with 1. So they will ask this question: after how many RTT window size will reach the maximum value? Okay, so here 6 RTT and here obviously 5 RTT. After 5 RTT, window reach maximum value. Okay, and just for the sake of practice, I will solve 1 or 2 more questions. Okay, take the snapshot. I will jump to the next slide. Done?
Yes, sir.
Okay. So now let us assume say WR is 16 kb, MSS is 1 kb. So same, they are saying after how many RTT? After how many RTT window reach maximum value. So and they will say slow start phase start with 1 MSS. So you will say okay. So first of all, you should convert everything to MSS. So WR is nothing but your 16 MSS, because MSS is 1 KB. So the WR is 16 MSS. So you will say 1, 2, 4, 8. So threshold will be what? 16 by 2. Now window R is 16. So 16 by 2, that is 8. So 1 to 4, till 8 we will go. Then 9, 10, 11, 12, 13, 14, 15 and 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you will say after 11 RTT, it will reach the maximum value. I think it's very simple, no? Any doubt?
No, sir.
Okay, so take the snapshot. I will jump to the next slide. Okay. Now let us assume, done?
Yes, sir.
Now let us assume window R is 32 KB and 1 MSS is 2 KB. Okay. And say I want to ask after how many RTT window will reach maximum value. So I have told you everything should be converted into MSS. So WR is 32 by 2, 16 MSS. So now I think everything will be copy pasted like this. 16 MSS I have just told you. So I 1, 2, 4, 8. Threshold will be 16 by 2, that is 8. So 9, 10, 11, 12, 13, 14, 15, 16. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So after 11 RTT, we will get it. Okay, it's very simple. So this is all about your slow start and congestion avoidance phase. So till what point we have slow start? This is slow start. And after that we are having congestion avoidance phase. Clear?
Yes, sir.
Okay. So let me jump to the next slide. Take the snapshot. So till now we have not discussed about congestion detection. There are 3 phases, no? Slow start, congestion avoidance and congestion detection. So now I will talk about congestion. See, I think you have got it now. Exponential increase, then linear increase. Slow start, exponential increase was there. Congestion avoidance, linear increase was there. So now I will talk about congestion avoidance phase. Okay. So what is congestion avoidance? So there are two ways. Sorry, congestion detection. Sorry for that. Last phase was congestion detection. So there are 2 ways to detect the congestion. 2 ways. One is the timeout and next is 3 duplicate ACK. I have just told you timeout can be done or 3 duplicate ACK come. When timeout is there, that means you have no longer received 3 duplicate ACKs. That means what? This means very high congestion. Okay, and 3 duplicate ACK means there is a mild congestion. But it is not always. See this. There might be a case that 3 duplicate ACKs are not possible. Okay. For example, you after sending, see this. Say if window size given is say 200, only 200. Okay, and sender is sending 100 byte segments. 100 byte it has sent sequence number 100, and it has sent sequence number 200. It has lost in the medium. Now there is no other segment to be sent, so only one ACK will come. That means ACK 200. No other ACK will come. So 3 duplicate ACK is not always possible. Are you getting it? So sequence number 100 it has already received. Just only one segment is lost, and still we will say we have very high congestion because of timeout. Okay, so it is just our assumption. My main concern is that do not think that timeout always means it is very high congestion, and it is not the case, because 3 duplicate ACKs might not be possible. Okay, sometimes it might not be possible. And why we are considering 3 duplicate ACKs as mild congestion? Because everything has been, see this, everything has been received, only one was lost in the medium. See this, sequence number 100 was received, then only 200 was lost, 3, 4, 5, everything was received, only one segment was lost in the medium. So that's why we are assuming that it is a mild congestion, it is not very heavy congestion. But in case of timeout, we will assume there is a heavy congestion, because 3 duplicate ACK might have come, but it has been lost in the medium. Okay, it might be the case they all have been lost, and these 300, 400, 500, everything has been lost in the medium. Then obviously timeout will occur. So our general assumption will be that timeout means very heavy congestion, but it is not always that it is very high congestion. There might be a mild congestion, but still we will consider very high congestion because of timeout. Okay, yeah. So here, anyhow, whatever may be the case, AIMD, additive increase multiplicative increase algorithm, will consider timeout means very heavy congestion, and 3 duplicate ACK means mild congestion. So what are the ways of handling? So in case of timeout, it will simply say, now threshold. Okay, in both the scenarios, let me tell you, in both the scenarios, whether it is timeout or 3 duplicate ACK, threshold will be window current, whatever is the current window value. Threshold will be window current by 2. Okay, and in case of mild congestion, we will directly start with that threshold value. Okay, that means we will directly start with congestion avoidance phase. But in case of very heavy congestion, we will start with slow start phase. That means start with 1. If you start with 1, that means very heavy congestion. If you start with congestion avoidance phase, that is mild congestion. Don't worry, you will not get it. When I will solve numerical, you will get more clarity. Take the snapshot, I will jump to the next slide. So basic theory, I think you have got it. So take the snapshot, I will jump to the next slide now. Done?
Yes, sir.
Okay, so basic fact is that for very heavy congestion, slow start phase will start. For mild congestion, congestion avoidance phase will start. And for both the scenarios, threshold will be window current by 2. So let me solve numerical now. Let us assume, okay, I think slides are over. So let us assume window R is 64 KB, MSS is 1 KB. So window R will be 64 MSS. And what will be the threshold? 32 MSS. Why 32? 64 by 2, that is 32 MSS. So window current we will start. So current window size, let me write it, window current. Initially it will be 1, then 2, then 8, then 16, then 32. After 32, because threshold has been reached, 33, 34, 35, 36 till 64 it will go. And then it will keep on with for 64 only, and so on. Okay, so this is what slow start phase, and then from here to here it is congestion avoidance phase. Now let us assume that when WC is 34, timeout occurred. Assume WC is equal to 34 and timeout occurred. What do you think? What will be now? Okay. So what we will say? I will start from beginning. 1, 2, sorry, 4 na. I have forgot to write 4. 1, 2, 4, 8, 16, 32. Double na. Huh. And 1, 2, 4, 8, 16, 32. Slow start is over. Now congestion avoidance has been started 33 and then 34. Now I'm saying at 34 timeout has occurred. Now since timeout has occurred, I will say window current is what? 34. So my new threshold will be 34 by 2, that is 17. And now what? I will start with congestion. I will start with slow start because of timeout. See this, I have told you. Slow start phase will start when timeout occurred. Slow start means I will again start with 1. Okay, then 1, 2, 4, 8 till 17. 1, 2, 4, 8, 16 and then 17. So this is slow start. After 17, then we will start with congestion avoidance phase. 18, 19, 20. Okay, and now let us assume here 3 duplicate ACK comes. 3 duplicate ACK. At 20, 3 duplicate ACK comes. So what will be our new threshold? Window current, that is 20. 20 by 2, that is 10. Now since 3 duplicate ACK, so now see this, in the previous slide I have written congestion avoidance phase will start. See, whatever may be the case, timeout or 3 duplicate ACK, threshold will be window current by 2. Okay, and in case of timeout, slow start will start. In case of 3 duplicate ACK, congestion avoidance will start. So I will start with congestion avoidance phase. That means from 10, directly from 10 I will start. 10, then 11, then 12. Okay, now let us assume again timeout occurred. At 12, assume timeout has occurred. Timeout means what? Threshold will be 12 by 2, that is 6. And now we will start with 1 again. Slow start 1. Now it is important. Please see, focus here. Threshold is 6 now. So till 6, a slow start phase will be there, and we will keep on doubling. 1, 2, 4. Now 8 we cannot go. We will go till 6. Why? Because till threshold we will be having slow start phase. See this, I have told you. 1, 2, 4, 8, 16. But 17 was not good value. That's why I am doing it again and again. After 16, obviously you might get 17. But you will say from 17 we have got congestion avoidance. No, it is slow start only. Because then after 16 we will go to 32. But 32 is not there. Our threshold is 17. So I will go till 17. Similarly here, 1, 2, 4. Then we want to go till 8, but 8 is not there. Threshold is 6, so we will go till 6. Okay, so 1, 2, 4, 6. And then we will start with 7, then 8, and so on. Okay, this is the case. Yeah, so take the snapshot. I will jump to the next slide. And okay, so here itself, let me give you some other idea. Okay, and let us suppose, I think you have got it, but still for satisfaction point of view, I will solve another thing. Like we are going till 64 na. So assume 64, then again 64, then again 64. We are 64 only. Now assume after sending this 64, timeout occurred. Are you getting it now? 1, 2, 4, 8, 16, 32, 33, 34, 35, and so on up to 64. Then we will keep on going 64, 64, 64 only till there is no, we are in congestion avoidance phase only, 64, 64, 64 only. And we might get some, you can say, congestion, or congestion means some timeout occurred or 3 duplicate ACK comes. Now I am assuming that timeout occurred at 64. So immediately threshold will become what? 32. Because window current was 64. So what you will say, 1, 2, 4, 8, 16, 32, and immediately after 32 threshold, you can say 3 duplicate ACK comes. So now threshold will become 16. So since 3 duplicate ACK, threshold will become 32 divided by 2, that is 16, and we will start with 16 only. In 3 duplicate ACK, we will start with threshold only because we are in congestion avoidance phase. 16, then we go to 17. Now a very important point is coming. Please try to focus here. Assume here timeout occurred. If timeout occurred, what you will say? Your new threshold will be what? 17 by 2. What should be the value according to you? Point. We cannot get a value in point. So we will take a floor value. That means 8. Okay. So now our new threshold is 8. So we will say now 1, 2, 4, 8, and then 9, 10, 11, and so on. That's it. So any doubt here?
No, sir.
Okay, so that's it. So this is all about your this additive increase, multiplicative decrease, AIMD. Very important. Many questions have been asked in GATE. Now you can solve every GATE question very easily. So the basic step is that whatever WR, whatever MSS is given, you try to find WR in terms of MSS, threshold also in MSS, and then solve. You will get the answer very easily. Okay. Take this snapshot. I will jump to the next slide now. Done.
Yes, sir.
Okay. Yes. Next is TCP timers. Okay. What are the timers in TCP? So there are total 5 types of timers. First is time wait timer. Next is keep alive timer. Next is persistence timer. Next is acknowledgement timer. Acknowledgement. Acknowledgement timer, and the last is timeout timer. So these are the total 5 types of timers which we have to study in TCP. One by one we will study. First is time wait timer. So let me clear you that. Take the snapshot. I will jump to the next slide. Done.
Yes, sir.
Okay. So what is time wait timer? See, we have client and server. So first phase is connection establishment by three-way handshaking. This is connection establishment. Then we have some data transfer, something go and out and so on. And then we will have connection termination phase. So connection termination can be done in three-way handshaking or four-way handshaking with half close. I have told you. Three-way handshaking or four-way handshaking with half close, whatever may be the case. After connection termination, these resources, that means buffer and so on, they remain allocated. Okay, it is not like that client and server, they will release their buffer immediately after connection termination. Okay, and some port number will be given to the client, some port number will be given to server and so on. So these port numbers are not yet freed. They are with associated with these client and server process. So directly I want to say, after connection termination, client and server are not killed. They are still there. Why? Because lifetime of the packet is, say for example, 3 minutes. So they will resources will remain allocated. client and server side remain allocated for 2 into lifetime of the packet. Now lifetime may be 3 minutes, lifetime may be 1 minute, whatever may be the case. For 2 into lifetime, these resources will be allocated, will remain allocated. Okay, and this is nothing but time wait timer. So time wait timer is 2 into lifetime. Okay, this is your time wait timer. Now question arises, why these resources are allocated? Okay, so it is just like that. For example, there is a house. Okay, you have rented this house for 1 month, say. Now after 1 month you will not immediately you can say empty this house. Okay, so you will need 1 or 2 days extra, so that you can transfer all the you can say whatever you are having, like almirah or clothes and so on. You need to transfer all the things. Okay, so for that you need 1 to 2 days. Now in those 1 or 2 days, some pending bills might come to you and you have to pay them also. So same is the case here. For example, if connection is terminated and all the resources have been deallocated, now for example from server side one packet come, because lifetime is 2 into lifetime of packet is a 3 minute. So 6 minute, for 6 minute client resources will be allocated. Okay, so for example from server side one packet come after say 2 or 3 minutes. Now client should be able to handle that. If client is not there, so for example its port number was say 56542, this same port number is given to some other client process. Initially it was given to C1, now the same is given to C2. Now C2 will receive that packet from the server and it might assume that it was its own packet and it might start processing it, but actually it was for client 1 which is no longer there. So for example you just emptied the house and you go and some other person come and he is paying your bills. Okay, it is not good na. You have not paid your bill and the other person which is coming in place of you in living started living in your house and he is paying your bill, because that will come after 3 to 4 days. So it is not good. So same is the scenario here. This port number was given to client number 1. Okay, and then this this client because of connection termination, this client 1 goes away, and now this same port number is given to client number 2. Now this client number 2 will receive packet from server assuming that it is its own packet, but it was related to client number 1. So that is the problem. So that's why time wait timer is used. Okay, so time wait timer is resources that client and server remain allocated for 2 into lifetime, and this 2 into lifetime is nothing but your time wait timer, so that if packet might have lost in the medium and something like that, so it might come again. So for that, for handling that packet, we have allocated this. Okay, yeah, so it is used. So in one line I should say keep track of late packets. It is used to keep track of late packets. And what is the value? 2 into lifetime. These are the two important points which you should remember for time wait timer. Take the snapshot. I will jump to the next slide. Done?
Yes, sir.
Next timer is keep alive timer. What is keep alive timer? See, actually server is handling request of many clients at a time. Client 1, client 2, client 3, client 4 and so on. And obviously there are limited resources with the server. Okay, so for client 1 it has allocated some amount of memory. For client 2 also it has allocated some amount of memory. For client 3, client 4 and so on. Since memory is limited or resources are limited, and let us assume the server has reached the maximum capacity, like it can handle n number of clients, and it has reached n number of clients. Okay, or n number of clients have made connection with the server. So now obviously server cannot fulfill request of n plus 1th client. So n plus 1th client will be ignored because it cannot fulfill its request. Now assume client 3 and 4, they have just made the connection, they are not active. They have just made the connection and they forgot, or they are doing something else. So obviously server should discard these connections now, so that it can be given to other clients. So how server will keep track of this? So for that, whenever client sends some data, whatever is there, either acknowledgement or data or something like that, server will start keep alive timer. Okay, and if it send if client send another packet like this, so it will again start this same keep alive timer. So keep alive timer is, say for example, say I will say 1 minute. Okay, so when client sends some data to server, server come to know, okay, client is active, he is participating something, so it will start 1 minute timer. Now before 1 minute timer expire, client send another packet, so it will start again, it will reset the clock for 1 minute, and so on. Now as soon as 1 minute is over, it will simply break the connection. It will say for 1 minute client is not sending data, it will assume client is dead, and it will terminate the connection so that it can be given to other client. That is keep alive timer. Okay. Any doubt? So it is rough way. Actually, when keep alive timer expires, it will not actually immediately release the connection. Rather, it will send probe packet. Probe packet means it will try to get the status of the client. Okay, actually it is not required for get. That's why I have not tell you. So you just know this fact that keep alive timer is used to check idle clients. Okay, whenever client is idle, server will you can say close the connection for the clients, and so that this some other client can make connection with the server. Okay, so if you want detail, then I will just give you a small hint. Okay, after keep alive, if keep alive timer expire, then server will send prop packets. Okay, and it will send one prop packet. Prop means asking, one prop packet. If still there is no reply, it will send 9 more prop packets, 9 more warnings, you can say. If still no reply, then it will terminate the connection. Okay, so total 10 prop packets will be sent, and after that it will close the connection, assuming client is dead. Total 10 prop packets will be sent, and still no reply, then connection terminated, assuming client is dead. Okay, this is the actual way. Okay, but no need to remember all these prop packets and all. You can simply assume that keep alive timer expired, then connection is terminated, assuming that client is dead. So the basic thing, whatever they will ask, they only one question have been asked in MSQ, so you should remember that keep alive timer is used to check idle clients. Okay, so if client is idle, that means it is no longer doing anything, so it will simply discard the connection so that it can be given to other clients. That's it. So this is all about keep alive timer. Next is persistent timer, but I think time is up. So from here itself, we will start the next class. Okay. So 3 more timers are left out: persistent timer, acknowledgement timer, timeout timer. Okay. Yeah. Okay, then if you have any doubt, you can ask me. Otherwise, I will wind up the class here itself.
No doubt, sir.
Okay, then. Good night.